Good morning, everyone. My name is Chris Tilley. I'm the CEO of SunLink Corporation, and I appreciate you taking the time to sit with me through a webinar on designing for wind. I'm going to spend a little bit more than 30 minutes talking about some of the implications of SunLink's research. We've spent about 7 years in the wind tunnel and doing a lot of R&D on wind. I'll talk a little bit about some of what we found and talk about put that in the context of how systems should be designed for wind. I'm going to focus largely on rooftop systems. We've done a lot of work on ground mount systems as well, and I can take some Q&A on that at the end of it, but just so you know, the main focus of this presentation is going to be related to rooftop systems. A general outline, I'll start off by talking a little bit about permitting today in the United States and what the building codes do tell us about that and what they don't tell us, and talk, again, a fair amount about some of our findings out of our wind tunnel work, R&D work, and then we'll open it up for Q&A. So if we start today and we look at the state of solar permitting today, we see a huge variation in what's required. Over the last 10 years, I've seen a lot of different things in this industry. SunLink has been involved in permitting approaching 2,000 large commercial systems throughout the U.S. in places like Puerto Rico, where there are very high wind loads, in places like Ottawa, where there are very high snow loads, in places like Los Angeles, where seismic is a big concern. And I've seen lots of different things. And the variation is not really good for the solar industry. On one side, I've seen very large commercial systems go in with only an over-the-counter electrical permit, where no structural engineering was checked at all. And that's pretty scary to think of the liability that might be accruing to the solar industry based on that type of permitting. On the other hand, on the other side of things, we've spent, there have been cases where we've spent tens of thousands of dollars and hundreds of hours answering every little question you could ever imagine from a permitting official or from an engineer, and that's not good for the solar industry either. And the reality is we need to converge on some sort of standards that create a safe environment for solar, but also make it economical for us in the industry to be able to put in solar and get it on more rooftops. I wanted to start off by talking briefly about what we're designing for. We're designing for very rare events. Large snow loads, 1 in 100 year, 1 in 300 year, large earthquakes, not even like Loma Prieta, but worse earthquakes, design earthquakes in that, or very, very high wind regimes, situations. On the right, we see Hurricane Irene that came up, a picture of that came up last year at the East Coast. There were about 300 SunLink systems that fell within the hurricane wind cone zone, according to NOAA, and I'm happy to say that all of them seem to do well. But it's important to know that we're designing for very rare events, and if over 2 or 3 years we haven't seen any failures, it doesn't necessarily mean that things were designed well for the code. And that's not what the intent of the design needs to be. It needs to be for these rare events. When we look for how we go about designing PV systems, particularly stuff on buildings, we look to ASCE 7 for guidance. And this standard, the minimum, as you see there, minimum design loads for buildings and other structures, is a standard that's essentially been adopted into the building codes, whether it be the California Building Code or the International Building Code. We all look to this standard for determining how do you design a rooftop or a building or cladding or foundations and those types of things. And what's important to note about ASCE 7 is that it provides essentially no real guidance for things like solar arrays. So it provides really good guidance on how you design a rooftop and tells you how you would do it on any type of building. It provides some guidance for rooftop equipment like the air conditioning unit that you see in the upper left-hand corner. But fundamentally, a solar array on a rooftop experiences very different loads than either of those two. And so it leaves a big open area for interpretation and a lot of anxiety and question marks both in permitting officials' minds and in engineers' minds. When we look out at what we've seen in the market, how do people deal with that? How are engineers and permitting officials dealing with that lack of guidance in the U.S. market? Well, one practice is to just treat the solar arrays as though they are the rooftop itself, and you use the loads of the rooftop as though it was the same as a solar array. And it turns out, based on our testing and looking at the values across a lot of different projects, that is not a bad way to go. It gives you actually generally safe results, conservative safe results, where you're designing for loads that are equal to, or in many cases much higher than what you really need to design to based on our testing. So that's the downside of it. The good side is it's safe, and it's even though a rooftop is not the same as a solar array, it gives you reasonably good design values and guidance, but it's overly conservative. So you'll end up with systems that need to be connected a lot more than they need be, or they'll be need to be a lot heavier than they would actually need to be. The second thing that we've seen out in the market is using some of the coefficients for rooftop equipment in the design of these systems. And this one is actually very scary for me, having seen some of these calculations. The main mechanism for things like that big air conditioning unit, the main mode of failure that people are looking at are overturning, large horizontal loads, pushing it and having it topple over and creating a safety hazard on the roof. Overturning of solar arrays is not the big issue. The big issue is lift and suction off the roof that can pull those modules off the roof and have them fly. I mean, drag is important as well, but you really need to deal with lift. And some of the calculations that you see for rooftop air conditioning units don't consider lift at all. So you can end up with systems that are horribly under-designed if you're not checking that value, and unfortunately I've seen some of that type of work. Finally, the area that really gives us some guidance is using the wind tunnel. ASCE 7 provides provisions for doing wind tunnel testing for things in which it doesn't have guidance, like solar arrays. So this is a natural way to go, and it's the right way to go, and a lot of manufacturers have done this. The problem is that there's a lot of complications there, and there's a lot of, it needs to be done appropriately, and I think that is a pretty significant issue, and I'll talk a little bit about that in just a second, about wind tunnel testing. But the key takeaway from this first part of this talk is that the current codes don't tell us what we need to know to design rooftop solar arrays. There really isn't good guidance given in the codes for this, for something that looks like a solar array on a rooftop. So how do we get there? Well, we get there the same way the code was developed, and a lot of other things have happened, and that's we do a bunch of testing, we put together a program, we do a fair amount of analysis, and we develop a practical design standard. And this has been the approach that SunLink's followed, and I'm going to share a little bit of the results of that. But let's start with wind tunnel testing. So the code provisions for wind tunnel testing in ASCE 7, there's a fair amount of guidance that is provided in there. There's a lot of things that are not specified, but there is guidance given, and there are a lot of people, there are a lot of things that are being done inappropriately related to wind tunnel testing. So I've outlined here in more layman's terms what needs to happen for you to have wind tunnel testing that is compliant with the code. And the first of these is that the test must be done in a boundary layer wind tunnel. What this really means is that the wind very close to the earth in the area where buildings lie and other things, people and solar arrays will typically lie, it has a very different sort of profile in terms of turbulence and wind speed and energy in the wind than you would find at 1,000 feet in the air. And so when you're designing a building, you need to make sure that those characteristics of the wind at that level are accounted for properly, that they're there in when you do the test. And you call a tunnel that can do that a boundary layer wind tunnel. Now, it turns out there are thousands of wind tunnels in the United States. Most of them are aerodynamic tunnels, and those are good for designing airplanes or other things, missiles, things like that. But for buildings, ASCE 7 is very, very clear. It needs to be done in a boundary layer tunnel. And in reality, there's only a handful of these tunnels in North America. They're very difficult to calibrate and to get to the point where you could use them for real design values. And so one of the first things that needs to be a requirement, any testing needs to be done in one of these tunnels. The second criteria that really follows from the requirements in ASCE 7 is that you need to have the wind flow model what's actually happening. And it turns out for solar arrays on rooftops, the building itself creates the most important features of the flow field. And so if you really want to figure out what you're designing for turbulence and vortices and other things that are created by the building itself. So if you look at a wind tunnel study and the building's not in the model, it may be okay for a ground mount system, but it's completely inappropriate for a roof mount array. And then the final thing that I would highlight that you need to check for in a wind tunnel study is that it needs to be done at the right scale, and this follows from the previous 2 points. The previous 2 points are followed with the idea that you can't have blockage in a wind tunnel. If you look in the upper right-hand corner of this slide, you'll see essentially the test section at the boundary layer tunnel at the University of Western Ontario. This is where we've done almost all of our testing, and it's one of the largest tunnels in the world, and it's certainly the largest ones in North America. And to do testing properly, you can't have a blockage ratio of more than about 8%. And what that implicitly means is that if you're going to have a building and an array in there, that you need to be at a scale of about 1 in 20 or higher. And if you're in a smaller tunnel, maybe it's 1 in 50. But if you see a wind tunnel study that shows they're doing 1 in 5 testing, or they're doing 1-to-1 testing out of a wind tunnel, it's not meeting the what's really required in ASCE 7 for wind tunnel testing, because these are the points that are required, and for good reason. The biggest issue, though, however, and this is probably the biggest one, the big elephant in the room when it comes to wind tunnel testing, is the fact that Method 3 was set up, and the ASCE is set up so that ideally you would test a model exactly of what you're putting in the field. So wind tunnel testing is done for high rises very, very, very routinely. And what you do is you model the actual high rise, and you may model some of the buildings surrounding it. And you put pressure taps or sensors on the cladding, on all the surfaces, and you put maybe a force sensor in the base to figure out what your foundation loads are, and you model that actual structure with the surroundings in the wind tunnel from different wind angles, and from that you get coefficients for design. The problem with that for solar arrays is that we can't, for economic reasons and time reasons, we can't afford to model every single array, and we can't afford to model every single building. And these can be quite varied. If you look on the slide, we've got a system right outside of a stadium, a very different sort of terrain and building structure and geometry. And then you have a standard warehouse below that. And you can have a 5-6-story building will have very different aerodynamics. So what we really need is something that we can generalize, do a series of testing, and then say we can apply it to any of these buildings. And that is actually a really big leap. That's not, while that's not prohibited by the code, it's not generally what people intended when they're looking at Method 3 of wind tunnel testing. So there is precedent for this, and the precedent really is the rooftops themselves. In the throughout the 70s, there was a lot of wind tunnel testing done on various building rooftops models, actually at the University of Western Ontario. That's why we went there. And those values formed the basis of how the design code values are generated for rooftops in the ASCE 7 code. So they tested a lot of buildings, but they didn't test every building. You can now use those coefficients to design, a building that looks very different than maybe what was tested. And the reason that works is because they did a lot of testing and they figured out what the design envelope should look like. What are the worst case scenarios and the worst case buildings? And they said, okay, if you design for that, we feel pretty comfortable that you're going to meet the same level of safety that we want. So when we started our testing program, we went to the University of Western Ontario that, again, did a lot of this testing for the ASCE 7 code for rooftops and said, we want a similar program for rooftop arrays. And it turned out that's a very, very extensive program. We spent, more than 5 years doing a lot of wind tunnel research work there. And just to give you an idea of the scope of this, we've run, over 1,000 tests on 75 plus building and array models. We've tested tilt angles for different systems from 2 to 35 degrees, which all change the load depending on what the tilt angle is. We've tested the height off the roof from being right on the roof to being as high as 4 feet off the roof. We've tested systems to see what the difference to loads are in row spacing between the rows of different arrays. We've tested setbacks from the roof edge, a lot of different ones. We've done a lot of work on deflectors and shrouding, and I'm going to talk I'll talk a little bit about that a little bit later, and ways to aerodynamically get better values, and the deflectors and shrouds is one way to do this. We've tested roof height. We've tested panel height. Is the system in the modules in portrait, or are they in landscape? And we tested in things that are even higher than that to see, what happens to the loads in all these scenarios. And we've tested combinations of all of those things to understand how they they interact. So that gives you a brief overview. I'll show you a couple pictures. This is a picture of our arrays, one where we're looking to see what effect ballast blocks under the array might have. This is one, systems that are from 40 inches off the roof to 16 inches off the roof. Here's one on shrouding, and this is I'll refer back to this in a second for an example, but this shows a 10-degree tilt system with a gap near the top for pressure equalization, which is one of the mechanisms that you can get loads down by, and a shroud or deflector that goes down close to the roof. And as you see the picture, we're testing, what happens if you use it in part of the array rather than the entire array. And we've done a lot of different geometry testing and a lot of this type of testing in the wind tunnel. Finally, I want to talk a little bit about the method that you do the testing. There are a variety of ways to do it. Some people use something called a flyaway test model, where you have a little model generated and you put it in a wind tunnel and you turn the fan up until you see some movement. And at that point, you say that's the failure speed at which the array moved. But the issue with that type of testing is that because the wind is stochastic, you have to do that same test several times to get some certainty around when it actually moved. So you do, and what you get out of that is one data point. When did it move? It moved at this fan speed, at this wind speed, and we know that. To do a generalizable program like we've done would be almost impossible to do with flyaway testing. You don't get enough information out of a given test. The way that's used much more commonly, and is the way that most things are designed in wind tunnels for civil engineering is pressure tap model. So we measure the pressure on the surfaces of everything in the test section. So we're measuring the roof surfaces on the module, the top and bottom ones. We're measuring deflector top and bottom ones if we're doing deflectors, and we're measuring the roof surfaces. We typically would have in our models between 500 and 1,000 pressure taps on these surfaces, and we're taking pressure readings at 400 hertz, about 400 times a second. We're pulling in a value, and we'll run it over several minutes. So what happens in one of our tests is we'll generate a lot of data, over 30 million data points for each one, and we've done almost 1,000, maybe a little bit more than 1,000 of these tests. So we've got a lot of data, and that data can be very, very helpful. And I want to give an example of that. We can begin to look at the time histories on these. And if you look at the picture that's shown here, it's a video, it'll run in a second, but you're looking at the pressure on the upper side of the array surface, on the module side, on the underside, and what the net is. And we're looking at a cornering wind, a cornering vortex. The blue is high suctions, and the red is down push. And one of the interesting things, as you can see there, is that you've got down push at the same time you have these very, very high suctions. So you've got a very complex sort of flow field in the array, and when you look at lots of different models, you begin to understand what the physics are. And this is really fundamentally important to be able to generate a design envelope that'll encompass all the different things that we're likely to see on rooftops that we can generalize to other buildings. So it's something that we've looked at a lot of this data, we've examined it, and what we come up with for design is essentially a design curve that encloses the extreme values that we've gotten out of the testing. And this design curve that you see on this graph is very, very similar to what we would have, you would see as an engineer for a rooftop curve. And it has some characteristics that are worth talking about. The first thing I want to say is I want to apologize a little bit for the fact that the axes aren't labeled, but the horizontal axis is in square feet, and it's square feet of area, of effective area of the module, right, of the wind area of the module. So if you look at 20 square feet on the horizontal axis, you would see, two data points. A negative, one of them's about a -1 and the other one's about a +1. These are GCCP coefficients that would fit into the code to give you an idea of what your loads need to be. And one of the characteristics of this curve that's really important to note, and I'll note again and again in different places, is the fact that over smaller areas like one module, you have much, much higher pressures that you have to deal with than if you're looking at an area over 100 modules. And this is a fundamental characteristic of a wind, and it's reflected in the way that we design for wind on other structures, whether it be cladding or rooftop surfaces. So if you're designing, for example, a fastener to the roof deck, it may have a tributary area. It may have an area that it's responsible for that's about 1 square foot. And the design pressure used for that may be, let's say, just as 100 PSF for that one fastener. If you're looking at the joist that covers hundreds of square feet, that's or beam that carries a lot of weight for a lot of area, you'll use a much lower pressure. Maybe you use 20 psf for something like that. Now, the overall load going to that joist is a lot higher than what it is to the fastener, but the pressure that you're designing for smaller areas needs to be much higher, and that's because in wind, you can have these localized, very, very high pressure areas, and they will not occur within a larger area simultaneously, statistically. So you don't have to design for that, but they exist. These small area gusts really exist, and the bigger ones exist as well. So when we're designing structures or rooftops, you're checking all of this. You need to check for the small areas, check the very high gust winds over small areas, and you need to check that the overall system has got the strength when you get out onto the right on this part of this curve and pull the coefficients down. So this is what the design curve basically looks like, and it becomes quite difficult to figure out how do we actually design a solar system based on this, particularly a ballasted system, which is pretty complex. And what the conclusion we've come to through our analysis and research is that you need to check these loads, the small localized gusts and the bigger gusts. And the way to do that, that we've done it, is we actually build like a finite element analysis model, a SAP model, a structural analysis package model of every subarray on every system that we sell. And once that model is in, and I'll talk a little bit about how we built that, we check it for gust loads. So we check the corners for small localized gust loads. We'll pull numbers off the left side of that curve and check against it. And we'll check the entire structure to make sure that we have the strength in the structure to handle that load. We'll also check larger sections of the array, and we'll check and make sure that we have the capacity to support what the wind design coefficients are really saying for this. So in order to get a model that we're confident in, we've done a huge amount of physical testing in terms of making sure that what that SAP model does is what happens in reality in the lab. Coefficients of friction are important. We've done a lot of testing on that. The yield curves and the strengths of different components and parts of the system are also important to make sure the model is accurate, and we've done a lot of testing over the years on those. The bottom line on this is that when you look at this, it is complex to check to make sure you have the capacity in the system. And it's not a simple calculation over one large area. You really do need to check the system to make sure that you're handling the smaller loads, the higher loads over smaller areas as well as the more generalized pressure over larger sections of the array. And just because it's difficult, and just because it's not that easy, we can't ignore it. We really have to look at the data, and we really need to be designing for it. So the key takeaway from this part is if you really want to use the wind tunnel section of ASCE 7 and generate a generalizable stuff that really can be used effectively across it, you need a really pretty good-sized test program. And once you have that test program, you still have to figure out how you're going to design when the array itself changes. The shape of the array changes. So on each project. So let me focus now a little bit on some of the conclusions from the testing and what the data and analysis are really telling us. The first thing it tells us is that the wind loads over very small areas are much higher than many in the industry think. If we look at the level of one module, and I'm going to go through an example in a little bit that will drive this point home, what the magnitudes of these loads are, but the loads on smaller areas are much higher than you would think. And even in reasonably benign wind zones or maybe a slightly aggressive wind zones, the loads can get higher than what 1703 is testing for, right? So just to add a little bit of context, much less in really high wind zones. So we need to be cognizant of the fact that over really small areas, we can measure very, very high wind pressures. The corollary, something that follows from this is that you really need a rooftop system, as a result, really needs to be very heavy or heavily connected if you're not sharing the load. So if you're trying to deal with just one module, you're inevitably going to end up with a very heavy system, or you're going to end up with a system that's connected everywhere if you really want to meet these design loads appropriately. The one exception to that, and the one way out of that, is that if you have a very strong, stiff structure that can carry out the localized loads. And we'll talk about that in a second in the example, but if you have one module that's being hit with a really high load, but it can get transferred out to the structure over a much broader area, then that is one way to be able to reduce what the loads are and reduce the number of connectors of the weight. But the point that's there is that you need strength and stiffness in your structure to be able to do effective load sharing. And this inevitably requires more metal and more structure. And without that structure, it needs to be very, very heavy, very heavily connected in order to meet the basic design requirements that really should be met. So I want to talk through an example to give you an idea of the magnitude of the loads that we're talking about here. This is an example. We have a white paper on our website that gives more detail on this. It was published in Structure Magazine in July with a little bit more detail. But we see an array up there in the left-hand corner of this slide. And this array is that 10-degree system which I showed earlier, which has got deflectors, rear deflectors everywhere, and gaps for pressure equalization at the top, and it comes down close to it. And these are the actual design coefficients that we've measured for that, pulled off of the curve, the design curve that you would want to design for, and applied to methods applied to the ASCE 7 code. And if you're looking, and I should also point out, this is a benign wind environment, a fairly benign wind environment. This is a 90 mile an hour wind environment on a 30-foot building with exposure C. And these are the values that you would get for an array that would shape this. And what I'm looking at here is going to look at, if you're going to design to check the structure around where the green line goes through here, how would you go about doing that? So if we look at one module, as you can see, if you want to meet the ASCE 7 requirements, it requires almost 32 PSF of ballast to keep one module down. A localized gust on one module in the design envelope would reach something that requires that much. Now, no one is designing with 32 pounds a square foot, in their arrays that I've seen. If you go out to 30 modules, you'll see it only requires 6.6. And this is the nature of that design curve that I showed, where you have high pressures for smaller areas, and you have much lower pressures for larger areas. If you go out to several hundred square feet, you can get numbers that are below, let's say, 5 PSF for ballasting an array like this. So, but they all happen. They all need to be checked because those small gusts happen, the high pressure smaller gusts happen, as well as over the larger areas. So if we look at this design example, and I'm going to take a number which is very realistic in this industry. Let's say that this array is ballasted with 5 PSF. So you've got 5 pounds a square foot under all of these modules. And we want to figure out how are we going to design along that green line. Well, if we go to the 9 modules and we say what's the load that needs to be designed for there, by ASCE 7 it really is a 12.7 PSF design pressure. So if we apply that, and we've only got 5 PSF ballast, that means that the supporting surrounding structure needs to provide the difference. And that's what happens when you load share. You don't have to deal with the 32 PSF in a module. You have to deal with it, but if you've got 10 pounds of ballast, you've got to come up with 22 pounds of extra support around it. So if we look at these 9 modules and we do the calculations, what you'll find is that along that green line, there needs to be about 8,000, almost 9,000 foot-pounds of torque resistance there. That's almost 3,000 foot-pounds of torque around a given module frame. If you're relying on the module frame to resist that, it's almost 3,000 foot-pounds per module frame around that edge. And this is in a fairly benign wind environment. This is not in, on the East Coast somewhere. This is a California-type wind environment. So those numbers are very, very large. And you either have to have the structure or the weight to be able to deal with it, or if not, the modules are seeing a lot bigger load than people might think. Excuse me. So the real-world implication for this is that the code level of design module frames are likely to see higher wind loads than module manufacturers expect or design for. This is potential liability for the module manufacturers, the engineers, the integrators, and owners. All of us in the industry have some potential issues here if we're not designing for the appropriate loads and we're not doing the proper calculations on these. The final thing I want to talk a little bit about, because it's used quite often in the industry, is this idea of shrouding or deflectors. We've done a huge amount of work on this and seeing how shrouds behave in various configurations. And they have some real advantages. And the real advantage is they lower the overall loads. They lower the coefficients for a shrouded system are lower than ones that don't have deflectors or shrouds. And so in that sense, they're very good. Typically, you'll see a reduction of 20 to 30%. Now you can see much higher ones, but the geometry has to be really well tuned, and the geometry is really, really important in these systems. And therein lies a lot of the problem, because one of the mechanisms that a shroud is using to reduce the loads is to keep wind from coming up under the system and impinging on the bottom of the module. And as long as the shroud is down really close to the roof, that's effective. But the second that you see any change in that geometry, the shroud coming up at all, or changing, that gap changing, you lose the benefit of those coefficients, and it actually gets worse. And so it can spiral out of control. It gets worse, and the coefficient gets worse, and so it comes up more, and it gets worse. And so you have a rather unstable environment unless you can control the gaps between the shrouds or the modules and the roof very, very, very tightly. And if you think about what I said earlier about these low localized gust loads and load sharing and the requirement that you want to load share, those things are somewhat incompatible, because if you put a small heavy gust on one module in the middle of an array and you're expecting the other modules around it to add the additional support, when you pull on that module, you're going to get deflection. You're going, whether it's a half inch, whether it's an inch, whether it's 2 inches or 3 inches, you're going to get some deflection before you get full support from the surrounding structure. And you can't really use the shrouding coefficients in a case like that, where you know that things are going to come up. It turns out that for systems that are not shrouded with deflectors, there's much, much less sensitivity to that coefficient, aerodynamic coefficient, with the gap changing. So if you're an inch off the roof or 2 inches off the roof or 3 inches off the roof with a system that's not shrouded, the coefficients are stable. They don't change that much in a reasonable range. So shrouding is really good, but if you're going to do it, you have to make sure you keep that shroud on the roof through that entire design curve. So ideally, if you put 32 PSF under each module, that would be fine. You can get the advantage of it. But if you're looking for support, then you need to be really careful about taking advantage of those. The other issue really is, can you maintain that type of tolerance on a roof? When we look at roofs in general, it's hard. Maintaining an inch of tolerance underneath something is a very, very difficult proposition, and one that I would say generally is almost impossible to do in the field. This is the reason that, at least at SunLink, we don't use deflectors that much, because the advantages gets weighed out if you have to add so much structure to keep it stiffly, or add so much weight to make up the difference. So the key takeaways sort of from this data is that people need to really begin to think about this. So what is the impact on warranties? What's the effect on performance for modules when they see this type of load? For system owners, this has implications for you. If you're counting on kilowatt hours over a certain period of time, you may or may not get it, through these events. For permitting officials, you know how people have to design roofs. You have to design wind for both the fastener and the joist and the beam. The same type of scrutiny needs to be applied to solar arrays in general. These structures need to be checked. And for installers, you've got warranty considerations as well. And over time, you probably need someone who can support you through permitting. We're taking a lot of this data and sharing it. We're actively involved in the different standards committees, and there are different things that are coming out soon. But this is what they're going to say. This data was done. We have some peer-reviewed journal articles going out on this as we speak. So there's a lot of work that we've done on this, and it will make its way into a code. And we all need to come together to find a way to design both safe systems that are also reasonably efficient to install and cost-effective to install. So before I leave, I want to just point out that there's more information on our website on some white papers. We've also done a really significant amount of work on seismic testing. There's a picture there of a full-scale shake table test that we've done at Berkeley. There's a nice video on our website that shows what happens when a couple of our arrays go through design-level earthquakes that are very, very intense shaking. That R&D work is now being published and shown, and I'd invite you to, the invitation will go out we're doing another seminar on seismic right after SPI. So with that, I want to thank everybody for taking the time to listen to this, and I want to open it up to any questions people might have. Just so everyone knows, I'm looking through the questions, and we're trying to put them. We're trying to get to them all, and I have with me Tim Henson, a structural engineer at SunLink, to help with this. So I'll be right back with the first question. So the first question, there's a question about the fact that we've moved from top-mounted module clamps in our core system back to a bottom-mounted system with Precision, our new roof-mounted product. And what's the reasoning behind moving back and away from this? Top-mounted clamps or bottom-mounted clamps both can work if they're engineered properly. So it becomes an issue of really trying to optimize around cost and around ease of assembly. They both can be done. I mean, I personally have a little bit of a bias towards nuts and bolts going through the back frame of a module, but both can be done well. So hopefully that answers that question. So there's another question about setback and how setbacks from the ridge and how close we can get to the edge of the roof and so on. Our testing really goes to about 4 feet from the edge of the roof. And I mean, we've done a little bit more other than that, but really the design coefficients only go that close. And there's some other practical reasons that you may not want to be much closer to the edge than that. We have people all the time that are trying to get closer to that. You have a lot of edge effects on these arrays that you need to be careful of. So, you know, we can support at this point really about 4 feet from the edge.
This is Tim. Another good question that came through was regarding states moving towards ASCE 710. At the moment, we haven't seen a lot of states move towards that. Most states adopt mainly the International Building Code to start, and it's the year of that code that then references the year of the ASCE 7 documentation. We're expecting a lot of states to move to ASCE 710 very shortly, but as of yet, we've yet to see any code officials or any states actually get to that part. For those of you who are out there and designing, the ASCE 10 wind loading is a little bit different. The wind tunnel testing that you do from the wind tunnel to get the GC sub P values are still all valid, but the way they kind of look at the wind loads and the wind speeds is a little bit different. So you definitely will need to take that into account when you're actually transitioning to that code.
There's another question on ground mount systems. We've done a lot of testing on ground mount systems, and perhaps that would be a good topic for a future webinar. Very, very similar methodology. You don't have the roof, you don't have the building, so it's simpler, but you do have a lot of issues about, you have the same characteristic of the wind where you have to design for locally high loads that might hit the array. You have different features depending on what the chord length of it is, the height off the ground, what the tilt angle is that you need to account for, what the spacing between the rows is. All of those things play in ground mounts as well. And ground mounts, when you get to bigger chord lengths, there becomes an issue that you really need to pay a little bit of attention to, which is eccentricity of the load. I mean, how much of the load is going to the upper part versus the bottom part of the array. And another topic that's related to ground mount and roof mount is the issue of zoning. We didn't talk at all about that, but the zoning for ASCE, the way that things work out for rooftops is a little bit different. Arrays have different characteristics in that. And so when you get into roof zoning, it gets to be a good deal more complex, and people need to be careful about just using zoning out of ASCE 7 because you know there are some tricky things that happen in that. So
we had another question come in regarding setbacks based on building height. The wind tunnel testing that we've been doing, basically, Chris has said we're looking at a 4-foot minimum setback from the edge of the face of the building. But if you actually look at a 17% or h over 17 as a height, for really short buildings, you'll be able to get really a lot closer to the face of the building than the 4-foot minimum. So 4-foot minimum is mainly for really short buildings, but when you start to getting to taller buildings, things in the order of 40, 50, 60 feet, then the h over 17 has a tendency to start coming into play. We did have another question come in regarding the SAP models that we use to design our systems, regarding using the module diaphragm as part of the model. Typically, we don't use the module diaphragm because they can change from. The actual stiffness of that diaphragm is really an unknown quantity, and we have a tendency to ignore that in our modeling.
Be a little bit more conservative. Each module is different. We want to be able to use everybody's modules as well, so we need to be a little bit careful about some of those assumptions. There's a question about the one-to-one modeling. It says, you mentioned that the wind tunnel modeling testing of 1 in 20 is recommended, that one-to-one testing is not meeting the requirements of ASCE 7. This seems kind of counterintuitive. Could you elaborate why a one-to-one wind tunnel model is not recommended? Thank you. So, with the exception of one caveat that I'll talk about at the very end of this, you can't physically meet the requirements of ASCE 7 with a one-to-one model. That's the problem, is that if you're going to model the atmospheric boundary layer, it needs to be in a boundary layer tunnel. If you go to the largest tunnel that exists in the world, and you want to put a model in there that doesn't block too much of the tunnel to meet the requirements, so the requirements also say you can't block more than 8% of the tunnel with your model. If you put those two things together and you add on to it that you really need a building in it, you can't get a bigger model in one of these things and meet those requirements. So the reality is that one-to-one testing would be great if you had a big enough tunnel to do it. There are other implications of that make it difficult, but that would be a great way to do it. But you can't. But there are no boundary layer tunnels like that. So that's why if you see a wind tunnel test report from somewhere and it says one-to-one, they have not met the requirements of ASCE 7 because it's impossible right now in the world to do that. Now the one big caveat I'm going to throw out is that there is a new wind tunnel that is being commissioned, or was very recently commissioned and supported by the Insurance Institute, that can do full-scale wind tunnel testing, and I don't think any design. I know that there's not been any solar array testing in that tunnel, and it's not. As I understand it, I'm not 100% sure as to whether it's fully calibrated or not. But at some point, we could do some type of one-to-one scaling or much larger scaling in that tunnel. But that is absolutely state of the art. It's a tens and tens of $1 million tunnel that is just coming online right now. So other than that, you can't. That's the problem with one-to-one models. How would you compare wind tunnel values to the building code? What kind of reduction? Well, it's a hard question to answer because it depends on what you're comparing it to in the building code. Are you comparing it to rooftop structures themselves? Are you comparing it to the equipment values? And how are those applied? So it's very difficult, and it depends a lot on the geometry of the system as well. Is it a 30-degree system? Is it a 5-degree system? There are so many different things that it's very hard to make a comparison. In some cases, you can, if you're comparing it to the rooftop values themselves, you can get substantially lower values than that for certain types of systems. So that's about the best I can do to answer that. I want to thank everybody. I think we've come to the end of the time, and I don't see any additional questions. So I appreciate everyone's time, and we look forward to seeing you at SPI.